Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.9, which is using the power series to represent the function. And so in the last episode, we talked about how the power series is a series that creates a polynomial that is used to represent a non-polynomial function. So we saw the power series represent e to the x, for example. We saw the power series represent sine x. And so what we're going to do is we're going to start off with our most basic power series. So the series from n equals 0 to infinity of x to the n. And if I was to expand out the first few terms, this would become 1 plus x squared plus x cubed plus x to the fourth plus dot dot dot. And so because this is a geometric series, right? And I can tell that because the r value, right, the r is equal to x. I'm multiplying by x every single time. I can find the sum of this series right here. I can say that s is equal to a sub 1, which is 1 over 1 minus r, in this case, 1 minus x, right? Now this sum, right, this infinite series would converge upon this function as long as the absolute value of the x was less than 1. Again, the reason why that's true is because the geometric series only converges when the ratio is absolutely less than 1. So hopefully that makes sense. And actually, if you look at this, that means that x would have to be in between -1 and 1, which would make this the interval of convergence. In other words, what this is saying is that this polynomial best represents this function on this interval here from -1 to 1. So hopefully that makes enough sense. That's a review from a review from the last lesson. But let's go ahead and recall for a second here that all of this time we've been doing power series, we've been using x as part of the power series. Now x is generally speaking an input if I wanted to find out an output value. So what we're going to start doing in this video is we're going to start replacing x with a bunch of things. And so, for example, if I was to give you a power series, like say from n equals 0 to say infinity of x to the n over n factorial, if I was to expand out as many terms as possible, or let's just say 5 terms, that'll become 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. And that would be like plus dot dot dot. Well, remember, this is supposed to represent some function, right? So I could actually say that f of x is equal to the infinite sum of this polynomial, whatever this polynomial is meant to represent. Now, if you remember what this was from the last video, totally fine. But what I'm going to do now is I'm actually going to plug in a 1 in for x. So what that effectively does, it effectively makes this n equals 0 to infinity of 1 to the n over n factorial, or in other words, the sum from n equals 0 to infinity of 1 over n factorial. Now, if I was to expand this out, right, again, we're just replacing the x with 1. That would be 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial plus 1 to the fourth over 4 factorial plus dot dot dot. Now, what I'm going to do next is I'm actually going to punch this into a calculator, and we're going to see what happens to our decimal values as we get closer and closer to large values. Give me 1 second, I'll load up the calculator. So here I am at my trusty TI Nspire. What I'm going to do now is I'm actually going to calculate the sum of the first several partial sums here. So the way I create a sigma is I go to this little MOI button right here. It kind of looks like one of those MOIs from Easter Island. And I go and select all my different options here. I've got my summation right here. So I'm going to go from n equals 0. And I'm going to end it at 0 just so I can get my 0th term here. Now, the way the fraction is going to get set up, if I remember from the blackboard, I believe it's 1, right, over n and then factorial. Because again, I believe what we did was we let n happen. We're trying to find f of 1, right? And so from here, if I just kind of hit enter, I'm going to get 1. No worries, that's just the sum of the 0th term. If I let n equal 1, I'll get the 0th term plus the first term, which is going to be 2. That makes sense. And if I keep letting n get the top bound here get larger and larger, let's say if I just go straight to 5, what I'm going to get if I hit Control Enter is I'm going to get 2.716667. If I let this number get even larger, say like 10, I'm going to hit Control Enter. I get 2.7182. And then what I'm going to do finally is I'm going to let n go to 1,000. And I should be converging upon a number that looks really familiar here, this 2.71828, and that is E. So what I've been doing here is I've been taking the power series that represents e to the x and plugging in 1 into that power series, giving me e to the 1. So the reason why I show you that is because I want you all to know that, like plugging in anything in for x, right, even if we had, say, a function like f of x equals x minus 2, if I was to find f of 3, that would just be 3 minus 2, right? So I would just replace the x with a 3. And that's going to be one of the fundamental tenets about this lesson, is that plugging values of x into my power series to manipulate it so that I can turn it into something else later on. So when it comes back to the quintessential power series, right, we have a power series for 1 over 1 minus x. And we know this guy is represented by 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. So what I'm going to do is I'm going to go ahead and create 1 over 1 plus x now. And the way I'm going to do that is I'm going to try and reference him back to my baseline function right here. I know that this is 1 over 1 minus x. So how can I create 1 plus x out of this? Well, what I can do to make this 1 over 1 plus x as much like the 1 over 1 minus x as possible is I can go and call him 1 over 1 minus negative x. Hopefully you notice that the negative and the negative would become a positive, so I haven't really changed the expression that much. And so remember here, in this expression, this top expression here was really 1 plus a thing squared plus a thing cubed plus a thing to the 4th plus dot, dot, dot. It just so happens that every time that thing was an x every single time. Well, this guy would behave no differently because he's still really 1 over 1 minus a thing. So that would be 1 plus a thing squared, thing cubed, and thing to the 4th. This time, though, what is filling the role of the thing? The thing is going to be the negative x right here. So this is negative x all the way through. So if I simplify this guy out, I'm going to get 1 minus x, and the negative will go away because he's being squared, so he'll become plus x squared. The negative will stay there because of the odd exponent, so what I have is minus x cubed plus x to the 4th, and then minus dot, dot, dot. Now, if I had to come out with a sequence generator for this thing, I could say the sum from n equals 0 to infinity. Now my series alternates, so I need to include the negative 1 to the n, and I believe it's just going to be x to the n. So hopefully that made sense. I'll be right back with the next example. The next manipulation I'm going to do is I'm going to turn this guy into 1 over 1 plus x squared. So what I want to do here is I want to go back to my baseline function here because this guy, his behavior is predictable. The baseline for this is 1 over 1 minus x, and that's really, again, 1 plus a thing squared plus a thing cubed plus a thing to the 4th plus dot, dot, dot. This guy's going to be the same thing. He's going to be 1 plus a thing squared plus a thing cubed plus a thing to the 4th. And so I just have to figure out how I can create this 1 over 1 plus x squared into the 1 over 1 minus x squared, into the 1 over 1 minus x rather, his image. So how do I do that? Well, I know it's 1 over 1, and I'm going to go and subtract a thing, but of course I want to figure out what's going to make this thing positive. The only way that's going to happen is if this thing is negative, and I'm just going to slam down an x squared inside, which would then cause each of these insides to become negative x squared. So what I get is I get 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. And if I wanted to come up with a series generator for this, I'd start at 0. and I would say negative 1 to the n times, looks like probably, in this case, I'm multiplying by x squared each time, so x to the 2n, or x squared to the n. So that'll be my sequence generator for this guy. So I'm going to go and clean him up a little bit. I'll go and clean him up a little bit, because there's something else I want to do with this. Now that we have the power series representation for this, what we can do from here is we can actually create the next power series through integration, because this guy will become tan inverse of x. And that's going to be the integral, so x minus x cubed over 3 plus x to the 4th over 4 minus x to the plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus dot dot dot. So let's go ahead and figure out a sequence generator for this tan inverse of x here. So looks like that's going to be the sum from n equals 0 to infinity. There's an alternator here. So now I'm going to do x. And since my slope is going up by 2 each time, I know it's going to be 2n. And if I plug in a 0, I need a plus 1 to keep him at 1. And the denominator always seems to match the exponent. So I can just use that and be done with tan inverse of x. All right, I will be right back with the next example. In this next example, I'm going to find a power series representation for this. Now, this is going to be probably one of the more heavy on the algebraic manipulation that I'm going to be dealing with here. So let's see if we can't turn them into something more familiar. So remember, right now, I want to keep in mind that the main power series that I have at hand is this guy, right? Again, I know what this guy power series is out into, and it's going to be this, right? So it's going to be some variation of this. So I feel like this x cubed over 2 plus x is going to look something like this guy. So the way I'm going to get him to do that is I'm going to kick out that x cubed and make him 1 over 2 plus x. And this is going to be the piece that I turn into the power series. And at the end, I'm going to multiply that x cubed back into all the terms individually. So what that looks like right now is I'm going to do x cubed times 1 over something. Now, ordinarily, this coefficient here, or this term, is usually a 1. It's not a 1 right now. So I'm going to go and factor out a 2 and make him 1 plus 1/2 x. That allows me to kick the 2 into here and get x cubed over 2 times 1 over 1 plus 1/2 x. Again, I'm just going to pay attention to the power series portion. So now I'm going to go into 1 over 1, and this is where I'm going to create the negative sign, right? The negative, and it's going to be negative 1/2 x on the inside times x cubed over 2. And what that gives me is it gives me 1 plus blank squared plus blank cubed plus blank to the 4th plus dot dot dot. And again, what goes inside those blanks? Well, every time it's this negative 1/2 x every single time. And so I'm going to go ahead and simplify that out a little bit. And I'm going to say this is 1 minus x over 2 plus x squared over 2 squared minus x cubed over 2 cubed plus x to the 4th over 2 to the 4th. Now notice that I didn't actually evaluate the 2 squared, the 2 third, and the 2 to the 4th. And that's because I'm going to try and come up with a general series for this. I'm going to go and create a sum from n equals 0 to infinity. I know this guy alternates, so I'll include a negative 1 to the n. It looks like there's always an n up top, and he's being raised to whatever power his index is. So this is n equals 0, n equals 1, n equals 2, n equals 3. Over, the 2 is always present, but it's being raised, again, to the same power as the x, so it'll be 2 to the n. Now, while I would normally be done, I cannot forget that this guy comes along for the ride. So I can multiply him in, and get the sum from n equals 0 to infinity of -1 to the n times x to the bases are the same, so I'm going to add the exponents. So I get n plus 3 over 2 to the n plus 1. And that ends up being my power series representation for that function right there. All right, I will be right back with the next example. In this last example, we are going to write this 1 over 1 plus x to the 7th as a power series. And afterwards, we're going to integrate this 1 over 1 plus x to the 7th from 0 to 0.5 correct to 10 to the -7th. And so this is going to involve quite a bit here. So the first thing I'm going to do is I'm going to handle part A, which is having to write this guy as a power series. So once again, I'm back to this almost looking like something that I know, right? And so I can go and just kind of demorph him into 1 over 1 minus x. And again, 1 over 1 minus x is 1 plus x squared plus x cubed plus ... So how do I transform this guy into that? Well, remember, it's 1 plus something, right? So it's really just 1 minus a negative thing. And that negative thing is going to be a negative x to the 7th. So what that allows me to do is it allows me to have 1 plus a thing plus another thing squared plus another thing cubed plus another thing to the 4th plus ... And again, what is that thing the whole time? Well, that thing is going to be the negative x to the 7th. Again, negative x to the 7th, negative x to the 7th, negative x to the 7th. And what that's going to give me when I simplify him out is it's going to be 1 minus x to the 7th plus x to the 14th minus x to the 21 plus x to the 28. So nothing really too crazy going on right there. So this is my expanded power series here, and then we're good. So from here, that was A. So nothing really too crazy there, just a simple replacement. I don't think anything too crazy was going on there. But now they're asking me to integrate 0 to 0.5 of 1 over 1 plus x to the 7th dx. So what does that get me? Well, what that really is it's really the integral from 0 to 0.5 of my 1 minus x to the 7th plus x to the 14th minus x to the 21 plus x to the 28th, and really ... all the way down to dx. So when I begin my integration, the 1, it's just going to integrate like a regular polynomial, right? And this is actually one of the advantages of expressing functions as polynomials, because polynomials are, for the most part, pretty easy to integrate here. So x to the 22 over 22 plus x to the 29 over 29, and then that'll be ... and that will be evaluated on the interval from 0 to 0.5. So what I'm going to do now is I'm actually going to evaluate this integral, at least a few terms of it. But hopefully, before I begin, hopefully it makes sense that anytime I plug in a 0 into the whole shebang of this polynomial, it's going to go to 0. And so that will then allow me to just plug in 0.5 as my piece here. So when I evaluate, I'm actually going to convert 0.5 into 1/2. So I get 1/2 minus 1/2 to the 8th over 8 plus 1/2 to the 15th over 15 minus 1/2 to the 22nd over 22nd, or 22 rather, plus 1/2 to the 29th over 29. Now I'm going to go and algebraically manipulate this thing, and again, there's a ... following afterwards. I'm going to go and algebraically manipulate this thing so I can try and find a general form for this series here. It's going to be 1/2 minus, now because the 1/2 is being completely taken to the 8th power, I can actually call them 1 to the 8th, which is just 1, over 2 to the 8th times 8. Hopefully that makes sense. This will allow me to establish the pattern of this thing a little bit better, and there's a reason why I'm going to want to find a general pattern or a general term, for this series here. So if I wanted to find the general term of this thing, it would be the sum from n equals 0 to infinity. And it looks like it's alternating, so -1 to the n. And it's going to be 1 over 2 to the, how do I get this 8 right here? Well, what I'm going to do is if I look at the numbers here, 8 to 15 to 22, the slope of those exponents, if you will, is 7. And I'll get multiplied by n, but I have to add 1 to it to become 8. If I plug in a 2, I'll get 14, plus 1 is 15. Plug in a 3, I get 21, plus 1 is 22. And of course, the number that gets multiplied is the same as the exponent, so I can use the exact same formula to find that coefficient right there. So why is this helpful? Well, remember, they're asking me to calculate this integral correct to 10 to the negative 7. So what they want from me is they want an error of less than 10 to the negative 7th power. Now, if you're wondering why I left such a huge gap there, it's because I did it on purpose. Remember, the actual error is always less than my error-bound term. Remember, that's that maximum wrongness term that I have, right? And ultimately, I'm going to end up with 1 over 2 to the n, rather 2 to the 7n plus 1 times 7n plus 1. That's going to be my final term, right? It's going to be my final term, but I don't want my final term. I want the error-bound or maximum wrongness term, which is always the term after the fact. So I'm going to go ahead and take my a sub n plus 1, which is my error bound. And in the context of this problem, that's going to be 1 over 2 to the 7 n plus 1 times 7 parentheses n plus 1 plus 1. So that's going to be 1 over 2 to the 7n plus 8 times 7n plus 8. And that's got to be less than 1 over 1 with 7 zeros. So 1, 2, 3, 4, 5, 6, 7. I'm going to flip both of them. And I'm going to say 2 to the 7n plus 8 times 7n plus 8 has now got to be greater than 1, 2, 3, 4, 5, 6, 7. I believe that is 10 million. So at this point, we've been down this road before. It's a guessing game. When you put it in the calculator, you'll get eventually n equals 2. You're going to want to go up to the n equals 2 terms in order to have an error of that small. So what does that mean? What that means is that for me to get an error that is that acceptable, I'm going to go up to the n equals 2. Now, what this doesn't mean, this does not mean 2 terms. It means to the n equals 2. Now remember, guys, this is n equals 0, n equals 1, n equals 2. So you actually want the sum of the first 3 terms in order to get what you are looking for. So that is going to be 1/2 minus 1 over 2 to the 8th times 8 plus 1 over 2 to the 15th times 15. Now, if we put that into the calculator, what I'm going to get is I'm going to get something. And so let's go and find out what that is. So that's going to be 1/2 plus 1 over 2 to the 8th times 8. And I forgot, that should be a minus, and then plus 1 over 2 to the 15th times 15. Okay, so if I hit Control Enter, I will end up with 0.499513. Okay, 0.4995. In fact, you know what? I'm just going to copy that guy in. I don't want to make a mistake here. So I will do that. And what I get is I get this number right here. I even got a little bit of the cursor right there. Sorry about that. And so that is my number, accurate to 10 to the negative 7. So hopefully that makes sense. We are using power series in a number of different ways, largely a lot of algebraic and calculus type manipulation. We're going to be plugging in stuff to manipulate. We're going to be anti-deriving, we're going to be deriving all kinds of power series to create new power series. So hopefully that makes sense. As always, please leave comments or questions in the comments area. I will see you all in the next episode.